Okay, so welcome back to this next video in which we are discussing the sympathetic nervous system's innervation of the heart and the effect of it. And we've already seen the inotropic effect. Now we want to see the positive chronotropic effect, which is achieved by acting on the sinoatrial node and increasing the frequency of action potentials generated by that sinoatrial node cells. Okay, right, so we are revising the sinoatrial node action potential so that we can understand how beta-1 adrenergic stimulation is going to lead to the quickening of the generation of these action potentials. Okay, so we've just discussed these T-type voltage-gated calcium channels. Now, these T-type voltage-gated calcium channels, they will be activated to open upon the depolarization of the electrical potential difference across this membrane to negative 60 millivolts, which is what the HCN channel has just done, basically. Brilliant. So they will now open. And they open extremely rapidly. So the instant you get to negative 60 millivolts, these channels will open. Now, the calcium concentration gradient, let's have a look at this. The calcium concentration gradient across the cell membrane. You have 1.5 millimolar concentration or thereabout in the extracellular fluid, and then you have 100 nanomolar concentration inside the cell. That is a 15,000-fold concentration gradient. It dwarfs the concentration gradients of sodium and potassium. They're pathetic compared to it. So, to be honest, you don't even need to ask what the electrical potential difference across the membrane is. This is a 15-fold concentration gradient. No physiological electrical potential difference across that membrane is going to be able to stop the movement of calcium into the cell when you open a calcium channel. Okay, so you open this T-type voltage-gated calcium channel, and what's going to happen? Calcium is going to move into the cell. So it's going to come into the cytoplasm of the cell. And when you move this calcium into the cytoplasm of the cell, calcium's a divalent cation. It has two positive charges. So it's going to raise the electrical potential of the intracellular compartment further and reduce the electrical potential of the extracellular compartment because we're moving the calcium out of the extracellular compartment. So this number here is going to go down. This number here is going to go up. So this one's becoming bigger, and this number that you're subtracting off is becoming smaller. So this overall number is going to become more and more positive. So what happens is you rapidly depolarize the electrical potential difference across the membrane. And it goes to just over 0 millivolts. So it just becomes positive. It just gets to the point where the intracellular electrical potential is greater than the extracellular electrical potential. And then these T-type voltage-gated calcium channels ruin the fun. Okay? They close. They close extremely rapidly. That's why they are the transient type voltage-gated calcium channel. They opened extremely rapidly, and then they closed. So they were only open for this tiny little period here, basically, and now they've closed. So the calcium stops coming into the cell. Okay? Right. So we've got to this positive electrical potential difference. Now what's going to happen? Well, we're going to go back down, basically. And the way we're going to go back down is that you're going to activate voltage-gated potassium channels. Well, actually, the voltage-gated potassium channels were activated long ago. It's just they were far less quick to open than the T-type voltage-gated calcium channel. So here in green is the voltage-gated potassium channel, which we will abbreviate to V for voltage, G for gated, K for potassium, C for channel. Okay, so the VGKC is going to open, and it was activated to open roughly at the same time as the voltage-gated calcium channel of the T-type. However, it took much longer to open, so just when the T-type voltage-gated calcium channel is starting to give in, it's closed, then this voltage-gated potassium channel starts to open, okay? And now, look at this potassium gradient. The concentration gradient in potassium favors the movement of potassium out of the cell. And also, the electrical potential difference across this membrane now has the electrical potential in the intracellular compartment greater than the electrical potential in the extracellular compartment. So in fact, the potassium wants to go into the extracellular compartment, at least for a while. Once we reduce the electrical potential back down, then obviously the electrical gradient will be against the concentration gradient. But even then, the potassium concentration gradient is still going to win against the electrical gradient. You'd have to take the electrical potential difference down to negative 85 millivolts, i.e. the intracellular compartment would have to be 85 millivolts lower than the extracellular electrical potential in order to get potassium actually not moving at all. Okay. So, when you open this voltage-gated potassium channel, what's going to happen is potassium is going to leave the cell. So you're going to move positive charge out of the intracellular compartment and into the extracellular compartment. So this is going to reduce the electrical potential of the intracellular compartment and raise the electrical potential of the extracellular compartment, because potassium carries a positive charge. Okay, so this goes down, this goes up. So this is getting smaller and you're subtracting off a number that's getting bigger. So this is going to become more negative. So indeed it shrinks back down, it repolarizes, okay? And it goes down to around negative 70 millivolts back again. And then these voltage-gated potassium channels, they start to close, okay? And you know what's going to happen now. You're back at negative 70 millivolts. So what's going to happen? The HCN channels are going to open again. Oh, and by the way, did I ever tell you about these closing? These will close once you start depolarizing the cell. So as you get this upstroke of the action potential here, when the T-type voltage-gated calcium channels are letting in calcium, these will close because they're only activated upon hyperpolarization. But when the voltage-gated potassium channels have repolarized the membrane, the HCN channels will be reactivated to open, and you'll get the same thing going off again. The exact same series of events will repeat themselves. And that's how you get a rhythmic generation of action potentials in these sinoatrial node cells. And what's going to happen is this action potential in this sinoatrial node cell will spread to the surrounding contractile cardiomyocytes, and those contractile cardiomyocytes will spread the action potential to their neighbors, and it will propagate on down the atria, and then through the AV node to the ventricles, etc. Okay, right. So, if we increase the frequency of these action potentials, then the heart will beat faster. How do we do that? Well, the way you can do it is by activating these HCN channels. If you increase the conductance of these HCN channels, i.e. if you increase the amount of sodium ions, the rate at which they bring sodium ions into the cell when they're open, then what will you do? You will depolarize this membrane quicker. If you're bringing in sodium faster through these channels, you will depolarize the membrane quicker because the sodium's coming in quicker. So this initial gradient here will happen steeper, basically. So if I draw another one of these graphs out, so here's another graph in which we are drawing the electrical potential difference across the membrane of our SA node cell, then if it's steeper, what will happen is you'll get something that looks like this. Okay? All the bits afterwards are exactly the same. All that's happened is this initial bit, this initial depolarization by the HCN channel is steeper, basically. Okay? And you can hopefully see that these action potentials take less time now. So the time interval between the start of an action potential and the end of an action potential here, this time interval is smaller once the rate at which this initial depolarization happens has gone up, i.e. this line's become steeper. So you can fit more of these into a minute. So, and if you have more of these action potentials, each one of these action potentials will cause the heart to beat. So you're going to get a greater heartbeat. So how do you activate the HCN channels to conduct a greater amount of sodium ions? Well, this is what the noradrenaline is going to do to the sinoatrial node cell. But we'll continue this discussion in the next video.